So in this video I want to ask the question, if phi of x is the arctangent, the inverse tangent of the ratio 1 plus x divided by 1 minus x, what is d phi dx? And I'm going to answer the question in two different ways. So the first answer is going to be using implicit differentiation, and what we're going to do is we're going to start off by taking the tangent of both sides in the above equation. So that means on this side we have the tangent of phi, which is a function of x, and on the right hand side we have the tangent of the arctangent, and that's just going to be the argument, so that is just 1 plus x over 1 minus x. And now we can differentiate it, and on this side we will use the product rule together with the chain rule for powers, and on this side we're going to use the chain rule, and this is because we're differentiating a function of x. And in this way, this is what we call implicit differentiation. We're going to be able to find the derivative of phi. And that may not be quite obvious for a moment how it's going to work, but we'll see. So let's differentiate first of all this side. Here we have a tangent, and the derivative of tangent is sec squared. So we're going to get sec squared of phi. Just to save a bit of room, I'm going to not explicitly write out that phi is a function of x, although of course it is. And then if we've differentiated this, we're going to get from the chain rule the derivative of the outside function multiplied by the derivative of the interior function here, and that is just d phi dx. And on the other side, we use the product rule together with the chain rule for powers. On the top we differentiate 1 plus x, and that is just going to be 1, and that's multiplied by 1 over 1 minus x. And then from the second term we have 1 plus x multiplying the derivative of 1 over 1 minus x, so that's going to give us 1 plus x multiplying, and now we have the derivative of 1 minus x to the power of minus 1, so that's going to bring a minus sign down, that's why I've put this here. We're then going to subtract 1 from the power, so we're going to have 1 minus x to the power of minus 2, and that means we can write it as 1 minus x all squared on the bottom, and then we have to multiply that by the derivative of 1 minus x, and that's going to be another minus sign, because we're going to get 0 minus 1, and that minus sign that multiplies this is going to make this plus. So we have two minus signs that end up giving us a plus sign. And then we put these terms together over a common denominator, 1 minus x all squared on the bottom, and on the top we're going to have here 1 minus x squared, and then from here we've already got the denominator, so 1 minus x squared on the bottom, so on the top we're going to have 1 plus x. So just to say it again a bit more clearly, here we have 1, we have to multiply it by another power of 1 minus x. So we get 1 minus x. What I've written so far is just the first term. The second term already has the correct denominator, so I just add plus 1 plus x, and I don't need brackets because I have a plus sign outside, so there's nothing to worry about signs. Putting these together, I see that the x's will cancel, and I will be left with 1 plus 1, which is 2. So therefore we have that d phi dx is going to be, and on the bottom here I have 1 minus x all squared, I have a 2 in the numerator, so that's just this side, but then here I had a sec squared phi, and I have to divide both sides by it. So I'm going to get 1 over sec squared of capital phi. Now this is true, but what we really want to do is to see if we can perhaps be a little bit more useful, if we can make this a little bit more explicit in terms of an x dependence. And the way we'd want to do that is by recalling that the tangent of phi is this ratio. And here we have sec squared phi. So at this stage it's useful to recall the following identity. Sec squared of phi is 1 plus tan squared phi. So on the bottom here we actually have, or we have 1 divided by 1 plus tan squared phi, and that is therefore 1 plus this ratio squared. So let me just write that out. So we have 2 over 1 minus x all squared, and then this second term is sec squared is 1 plus tan squared, so it's 1 plus, and tan squared is the ratio 1 plus x over 1 minus x, that's the tangent, and then we square the whole thing. So at this stage we're almost finished, but clearly I'm going to have to make a little bit of room, so I'll just pause for a moment. So what I do now is I realise that I'm multiplying here a fraction by another fraction. In the numerator I have 2 times 1, that's easy, and on the bottom I multiply 1 minus x squared into this sum of terms. When it multiplies the 1 I get 1 minus x squared, and here I have plus, and now this is 1 plus x all squared over 1 minus x all squared, and the 1 minus x squared here on the top will cancel there when it multiplies this part of the bottom with this factor of 1 minus x all squared. So what I'm going to get is therefore that d phi dx is 2, that's our numerator, over 1 minus x all squared, that's from this multiplying the 1, plus, and then when this multiplies this ratio, the 1 minus x squared and the 1 minus x all squared here will cancel, and I'll be left with the numerator here, 1 plus x all squared. So that's 1 plus x all squared. And now when we expand this, we're going to have here 1 minus 2x plus x squared plus 1 plus 2x plus x squared. So the cross terms, the minus 2x and the plus 2x here will cancel, and I'm going to have 1 twice over, and I'm going to have plus x squared and plus x squared twice. So I'm going to get 2 divided by 2 plus 2x squared. The 2's will therefore cancel, and we have our final result that d phi dx is equal to 1 over 1 plus x squared. And that is our final answer for this question. Now what I'm going to do is move on to the next slide and see on the second slide how to do this question in a slightly different way. So the second approach to this calculation of the derivative of phi is to leave this as an explicit equation. And this tells us that the derivative of phi with respect to x is going to be the derivative of arctan using the chain rule multiplied by the derivative of this ratio. And the derivative of arctan is 1 over 1 plus whatever is in the argument squared multiplied by the derivative of the argument. So all I'm doing here is using the chain rule. And what was the argument? It was 1 plus x over 1 minus x, and here 1 plus x over 1 minus x. So we will leave the first factor here as it is at the moment. So this is 1 plus x over 1 minus x all squared. Here we just repeat the calculation that we had used a moment ago. So we differentiate the numerator and leave it over the denominator. So that's just going to give us 1 over 1 minus x. And then for the second term we have 1 plus x. We're differentiating 1 minus x to the minus 1. So we reduce the power by 1, that means 1 minus x all squared. and there are going to be two minus signs, one from the power and one from differentiating 1 minus x. So that's going to give us all a plus sign. We put this on a common denominator, 1 plus x over 1 minus x squared in front, and then here we have 1 minus x all squared, and on the top we have 1 minus x plus 1 plus x. So we see that the x factors here are irrelevant and cancel. We're left with a factor of 2 on the top. We multiply all of this out just as before on the previous calculation. There's no great point going through it again, and what we arrive at is 1 over 1 plus x all squared, and that is our result for this calculation. To conclude this video, I want to answer a question which you may have asked yourselves. You know that the derivative of arctangent of x is 1 over 1 plus x squared, but we've also got that the derivative of the arctangent of 1 plus x over 1 minus x has also got the same value, 1 over 1 plus x squared. So how can that be the case? We're going to look at that on the last slide. So just to restate what we've seen, if phi is the arctangent of this ratio, we've shown that its derivative is 1 over 1 plus x squared. But we know the standard result that if u is the arctangent of x, then du dx is also 1 over 1 plus x squared. So if two functions have the same derivative, this generally means that the functions must be the same up to an additive constant. So the results we have till now imply it must be that phi is the same as u up to an additive constant. We can see whether this is the case by putting in some values. So let's, for example, look at the following. Let's say that x is equal to 0. For x is 0, u of 0 is going to be the arctangent of 0 from the definition of u in terms of x. The arctangent of 0 is 0. Phi of 0 is going to be the arctangent, and now if we look at the definition of phi, if x is 0, we have 1 plus 0 over 1 minus 0, so we have 1 over 1, and that's 1. So we have the arctangent of 1, and that is pi over 4. So therefore, we conjecture that phi of x is equal to u of x plus pi over 4. And you can verify this conjecture, or at least check the conjecture verifies too strong, by putting in some other possible values of x, such as, for example, x approaching 1 or x approaching minus 1, just to see if you can see that this relationship works for them as well. So, why might it be the case that this holds? If it does, it is certainly immediately the case that d phi dx would be du dx plus 0, because the derivative of a constant vanishes, and that would agree entirely with what we have seen here. So, assuming it's true that phi of x is u of x plus pi over 4, what can we do to verify that this is the case? Well, we know that phi is this arctangent, so therefore we know that the tangent of phi is this ratio. Similarly, if u is the arctangent of x, the tangent of u is just x. So we can look at some angle formulae for the tangents. So the tangent of phi is going to be the tangent, if our conjecture is right, of u plus pi over 4, and the formula for the tangent of the sum of two angles is that it is the tangent of the first angle plus the tangent of the second angle divided by 1 minus the product of the tangents, so here the tangent of u multiplied by the tangent of pi over 4. Now the tangent of pi over 4 is 1, so therefore what we have from this equation is that the tangent of phi will be the tangent of u, which is x, so that's x, plus 1 over 1 minus x. So here we have x times 1, which is just 1 minus x overall. So therefore, just changing the order of the terms around in the numerator, tangent of phi is indeed 1 plus x over 1 minus x. And that's exactly what we thought it would be. It agrees with our conjecture up here. So therefore we know from what we've done here that our conjecture is correct, and this explains why it is the case that the derivatives of these two functions are the same. And with that I will end this video.